All right, hello everybody. We're going to go over the exam here. I'm going to share my screen so we can start. We'll look at the exam. I'm going to go over the answers. This will be for version A. If you had version B, your answers might be, a different number, but otherwise everything should pretty much be the same. So hopefully this will let what's the key, what you got wrong, what you didn't get right. Um, or what you got right and why, and you can figure all that out. So we'll start with question one here. Iron turning to rust would be an example of. So a physical change and chemical change. Remember, with a physical change, the substance itself should still be the same chemically from one side of that change to the other, whereas with a chemical change, it will have changed in some way chemically. It'll be a different thing, different compound, or whatever it happens to be. So in this case, iron turning to rust. We know iron is a metal. We can find that on the periodic table. That's Fe. That's shiny, silver color, very hard. We know rust, though, is a different color now, very brittle. So chemically, this is a different thing. We're going from just iron Fe to iron oxide specifically. This would be a chemical change. Which of the following would be an example of an intensive property? So an intensive property is something that is internal to that substance. It doesn't matter how much or how little of that thing we have. Mass is an extensive property. It does matter how much we have. If we have a small amount of something, it will have a lower mass than if we had a large amount of that same something. Same is true for volume. Whereas with density, density is an intensive property because it does not matter how much of that substance we have. If I have a little cube of silver or a large cube of silver, the density of silver is specific, and the density of silver in the little cube or the large cube would be identical. And the same is true for boiling point. If I have a small cup of water, the boiling point of the water in there is 100 degrees Celsius, and if I have a large jug of water, the boiling point for the water is still the same. So both C and D are the intensive properties for answer 2. 3, if I had a metal cube, let's see, jump back into, no, not that. There we go. Okay, so if I have a metal cube with 2 centimeters per side, now that's 2 by 2 by 2, so it's a cube, and we know its mass. Then we want to determine the identity. And you have some densities listed on that last page there with some of your other constants. So what we really are looking for then is the density of this metal. And density is mass over volume. We have the mass. We don't exactly have the volume, but we do have the dimensions of this cube. So if we know the length, the width, and height of it, we should be able to find the volume. So I'm going to take that 2 centimeters and I'm going to multiply that 2 by times 2 times 2, or I can take 2 centimeters cubed, and I should see that its volume is 8 cubic centimeters. And then if density is mass over volume, and all the mass over volume or densities we have in the back are grams per centimeter, so then I can just take that 154.4 divided by 8. And when I do that, I get a density of 19.3 grams per cubic centimeter. And if we look at all the different metals in the back, we see the one that has that same density or is very close to it is tungsten. Which would be the greater mass. So we have 3.6 times 10 to the 6 milligrams, 1,123 grams, and 1 kilogram. What I would do is get all these into the same units to compare. So 3.6 times 10 to the 6 milligrams, there are 1,000 milligrams in a gram, or so I should say this would look like this many milligrams or this many grams. And then there are 1,000 grams in 1 kilogram. So 1 kilogram would be 1,000 grams. And we can see out of all these, when they're same units, grams, 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 That's our largest value there, A. All right, next. You have a height of the ceiling is 3.35 meters. Your friend measures the ceiling and gets these values, 2.91, 2.89, 2.90, 2.89. So there's very little range within these values. These are all very, very, very close to each other. So I would say that this has a high level of precision because of that, but they're still all relatively far away from the actual height of the ceiling. They're not super close to the true value, so I would call this not accurate. All right. Go back to our exam. Question 6. Which subatomic particles are contained in the nucleus of the atom? And that's just the protons and the neutrons. They make up the nucleus, and the electrons essentially can orbit outside of that. 7, what does X represent in the following symbols? So what I'm looking for is the value there on the bottom left. Should be the atomic number. That should be selenium in this instance. Which chemical symbol best represents an atom or ion with 38 protons, 50 neutrons, and 36 electrons? So again, protons dictate what the element is. So I'd go to the periodic table. I'd have to find the element with 38 protons or atomic number 38. That should be strontium, Sr. And then I'm not really worried with the neutrons here. I just want the chemical symbol, but we do have less electrons than we do protons. We have 2 less, so we should have strontium specifically with a 2 plus charge. So that was the answer you're looking for there, Sr 2 plus. Which group in the periodic table is known as the halogens? So if you're talking about main group elements, then you'd have 1A, 2A, you'd skip the transition metals and then go to 3A, that'd be boron, aluminum. So this halogens would be 7A, or if you're counting every column of the periodic table, counting the transition metals as well, then you'd be looking at column 17. So that's the halogens: bromine, chlorine, fluorine, iodine, etc. All right, element X has 2 isotopes. Okay. One with an abundance of 63.36%. Now we only have 2 isotopes, so I know they have to add up to 100%. So if I subtract the abundance of 1 isotope out of that, that will give me the abundance of the other isotope, 36.64%. And then we know the mass of the first isotope. So to get the weighted average, what I would do is I would take the mass of 1 isotope, I would multiply it by its abundance as a decimal, and then I'm going to do the summation of this for all the isotopes that I have. In this case, we only have 2. If we had more than that, though, we would have, isotope 1 times abundance plus isotope 2 times abundance plus isotope 3 times abundance, etc. Well, now we don't know the mass of the second isotope, so I'm going to make that Y. We do know the abundance. And then this will all be equal to that weighted average or atomic mass from the periodic table. And in this case, we do know that. That's 102.957 AMU. So I can carry out the portions of this that I do know. I really only have one variable or one part that I don't know. If I carry out this operation, this should give me 64.110816 plus, and then we still have there our Y times 0.3664 equals that 102.957. Now I want to isolate my Y, my variable there. First thing I'm going to do then is subtract this from both sides. And if I do that, of course, I'm going to lose it on the left side. And over here I get 38.846184 remaining. Now, since I have y times 0.3664, to remove that on the left side, I would divide by 0.3664. And whatever I do on one side, I have to do on the other. So doing this will cancel that there and give me now that y is equal to 106.021. If we're going with 4 sig figs, that'd just be the 106.0 AMU. Which would be the empirical formula for C6H12O4. So I'm looking for the smallest representation of this ratio. Looks like between 6, 12, and 4, the best I can do is dividing by 2. So if I divide all of these by 2, what I'm going to get for my empirical formula is C3H6O2, and I should see with that, I can't reduce that any further. All right, temperature of 243 Kelvin would be what in Fahrenheit? So easiest way I think here is to go from Kelvin to Celsius and then to Fahrenheit. Now, 273 Kelvin is the same as 0 degrees Celsius. So what I'm going to do for starters is take that 243 and I'm going to subtract 273 from that, and that's going to give me negative 30 degrees Celsius. Then, if I remember, 0 degrees C is equal to 32 degrees Fahrenheit. So if I can't remember, do I need to add or subtract the 32 first? Or do I need to multiply or divide by 1.8? A lot of times this will help me. Because I know if I add 32 to 0 first and then multiply by 1.8, I'm going to get a number greater than 32. So what I would have to do first is take 0 times 1.8 gives me 0 plus 32 gets me to here. So that's what we're going to do here. Negative 30 times 1.8. That's the conversion between Celsius and Fahrenheit. Every degree Celsius we go up, we would be going up 1.8 degrees Fahrenheit. And then at the end, we're going to add 32 to that. So we get negative 54. We add 32, and we get negative 22. You could do 273.15 if you want. You'll get, something just a little tiny bit different than this, 22 or negative 22.5, something like that. But out of all your answer choices, obviously, that's the only one that's remotely close. So you go with that negative 22. What would be the formula for calcium bromide? So we're going to go to our periodic table. We're going to find calcium. Now that's a group 2A element. What that means is it wants to lose 2 electrons to become like the next nearest noble gas. So calcium as an ion should take on a 2+ charge. We go and we look up bromide. That's group 7A or 17, depending on what type of periodic table you're looking at. But that's very close to the noble gas. What it wants to do is gain a single electron, become a bromide anion with a negative 1 charge in this instance. And then I'm just looking at how do I balance out those charges. I could either say, I need 1 2+ charge and then 2 negative 1 charges to balance that out. I could crisscross these values, but either way, you should see that this would be 1 calcium, 2 bromide would be the ionic formula for this compound or a compound with that name. And it's ionic also from the name because you have a metal and a non-metal. All right. 14, a covalent bond is best described as the sharing of electrons between atoms. Bond between a metal and a non-metal, like we just said, is what you're going to find for something ionic. Ionic compounds have a complete transfer of electrons. One thing completely takes them, the other completely loses them, or the bond between a metal and a polyatomic ion. So if we had whatever, here we go, like magnesium and nitrate, or maybe sulfate would be better. There we go. That's better. So there's my polyatomic is the sulfate, but This still has a negative charge. We're dealing with two ions here. So the bond between these two would be an ionic bond. So the only option there is a sharing of electrons between the atoms. So two or more nonmetals, they share electrons across that bond. That's a covalent bond. What's the name now? We have Cu, SO4, and 5 of these guys. Copper is a transition metal, so it can take on different charges. However, sulfate is a very specific polyatomic ion. It cannot take on different types of charges. So I know it has a 2- charge, and I know I only have one copper for every sulfate. So that means the charge on the copper has to balance that out. So it would have to be a 2+. When I write the name, I'll indicate that charge in Roman numerals. I would say, hey, this is copper 2 sulfate. And then we have these waters at the end, which we call hydrates. So I'd say hydrate. And then I need to tell you how many waters we have. And the prefix we use for 5 is penta. So that's why we have the copper 2 sulfate pentahydrate for that question there. Hydrocarbon. Okay, so we've got hydrocarbon. It's carbon and hydrogen only. We know the percent of hydrogen is 17.35% by mass. And then the only other thing again is carbon. They have to add up to 100. So if I take 100 minus the percent of this that's hydrogen, I'll know what percent of this is carbon. And then I can start to work with this. Now, I can't compare their masses directly because hydrogen has a different atomic mass than carbon. So all I need to do is get these into moles. Well, again, if I assume I have a 100-gram sample and 17.35% of that is hydrogen, then that would mean in a 100-gram sample of this hydrocarbon, 17.35 grams of it would be hydrogen. And to figure out how many moles that is, I would divide that 17.35 grams of hydrogen, the molar mass of hydrogen. Grams will cancel out, and we'll be left with moles of hydrogen. In this instance, 17.212 moles of hydrogen. Got to do the same thing for the carbon. So again, assuming a 100-gram sample, then 82.65 of those grams will be carbon. Divide by the molar mass of carbon. And we'll see how many moles of carbon we have. And we get 6.882 moles of carbon. So my empirical formula is going to look like this. But I don't have any whole numbers. That's kind of ugly. I don't really like that. I'd like to get it into whole numbers. So what I'm going to do is divide each of those number of moles by the smallest value here. Of course, when I do this for carbon, it's going to give me a 1. And when I do it for the hydrogen, it's going to give me 2.5. So we're not quite the whole numbers, but we're closer. That 0.5 tells me that's a fraction. 2.5 is the same as 5 halves. And if I want to get rid of that half, what would I do? I would multiply it by 2. So we're going to do that. Seeing that 0.5 tells me, hey, let's multiply this whole thing by 2. And if I do that, I get C2H5 as my final answer there for my empirical formula. All right, how to report this to the correct number of significant figures. So we have 965.43 minus 3.9111, and then times 941.341. So we'll carry out the operation in the parentheses first, and we get 961.5189. Now, Technically, we're going to use the rule here for addition subtraction, which is the least number of digits after the decimal. This has 2, this has 4, so my final answer is going to stop 2 digits after the decimal. So in reality, the 961 and the 51 are significant, but no other digits are significant. So this has 5 significant figures to it. I do not want to round yet because the problem is not done. So I'm going to keep the entire value. I'm going to multiply that by 941.341, and we're going to get 905,117.1628. Rule for multiplication is the least number of significant digits. Well, this only has, there we go, 5, and this one has 6. So our final answer should only have 5. So we should go out to there. But we've got that 7 at the end, so do I write this as 905,120? That 0 at the end there is technically ambiguous. So what I would like to do ideally to show this as being only 5 significant figures, but also expressing that it's 905,000, I would write it as, in scientific notation, 9.0512 times 10 to the 5th in this instance. There. How many moles of aluminum are in? So we have aluminum carbonate, and we have, for one version, it was 100 grams. For the other version, it was 200 grams, but you'll set it up the same way. So I need to know for this aluminum carbonate, how many moles of aluminum carbonate do I have in 100 grams? So we'll figure out aluminum's 26.98. So we take that times 2. Plus we have 3 carbonates, which means we have 3 of everything inside of there. So I have 3 carbons. Oop. And then 9 oxygens. So when we do all this, we should get something like 233.98 grams per mole. Okay, so I'm going to take the mass that we do have, the 100 grams, divide it by that 233.98. And we're going to see we have 0.4274 moles of aluminum carbonate. So I have that many moles of the whole thing, but when I start looking at individual elements, it's a different amount. So remember, for every 1 mole of this that we have, I have 2 alumina. So I would need to multiply this in this instance by 2. So we have 1 mole of, or 0.427 moles of aluminum carbonate, but 0.85 moles of aluminum. And that's what we were interested in. I'll give the correct formula for dinitrogen peroxide. So I've got di and nitrogen. Now the name of the first element stays unchanged. So I just find nitrogen in the periodic table. And then I've got pentoxide. So for this one, the normal name from the periodic table, it drops its ending and gains IDE. So what I'm looking for is oxygen in the periodic table. And then the di in front of the nitrogen tells me there's 2 of them, and the pent in front of the oxide tells me there's 5 of those. All right, and then very last problem. If I have 2.189 times 10 to the 22 lead atoms, what's the mass in grams? So easiest way to do this, I can find lead in the periodic table. I can find its atomic mass. If I scale that up to an entire mole of the substance, that's not its mass in AMU, but its mass in grams. So 1 mole of lead should weigh 207.2 grams. So now what I need to do is find out, well, out of the many lead atoms, what fraction of a mole is that? Just like if I told you, a dozen ball bearings weighs 50 pounds, then I told you I had, 4 bearings, you'd say, oh, that's a third of a dozen, so I'll take 50 times 1/3. We're going to find out what fraction of a mole this is. And to do that, I'm going to take the number of atoms that we have. I'm going to divide by Avogadro's number. And that's going to tell me, how many moles do I have? Do I have 1 mole, 2 moles, a half a mole? So when I do this, I get 0.03635 moles. And then now that I know the molar mass, I can just take that times the molar mass. Moles cancel. And we get our mass, 7.53 grams. And again, we know 1 entire mole is 207, and we have something less than a mole, or really less than 1/10 of a mole. We know it should be somewhere probably under 20 grams. And it is. It looks correct there. All right, so that's everything. If you have any questions, please feel free to reach out, office hours, or shoot me an email. If you think there's an error, please stop by my office hours. We can pull the Scantron. We can double check it. If the Scantron was graded incorrectly, we'll get you back those points. Otherwise, I'll see you next Monday.